The lesson objective for today is A.6F. Interpret and predict the effects of changing slope and y-intercept in applied situations. We're going to look at a few examples of some different applied situations and see exactly what changes to the slope or y-intercept do to our scenario. Here, the first example says the graph on the left below shows the number of miles that a car can travel with a given number of gallons of gasoline. The graph shows a car with a rate of 25 miles per gallon. Sketch and label a graph that best represents the number of miles that would be made at a rate of 20 miles per gallon on the grid on the right. So we can see what they're talking about here with this first graph. If you take and go over 1 gallon, and then follow this up till it hits the line, okay, you can kind of see it's going to hit about the middle of these two marks. Well, if the first mark is 10 and then it skips a mark and the next mark is 30, that means that the mark in between would be 20, right? So you can see this is 25 miles for 1 gallon of gasoline. And so you can even see that a little bit clearer here. And at 2 gallons of gasoline, you got 50 miles. So they're asking us to create on this graph over here one that would go 20 miles per gallon. So we're going to start with the same labels. We're going to have 1, 2, 3, 4, and 5. And just like before, that's going to be our gallons. Alright, and on this side we'll label it the same way. We'll have 10, 30, 50, and 70. Alright, and so if we want to show a vehicle that goes 20 miles per gallon, then that means each time we go over 1, we need to go up 20. And so that would put us right here. Go over 1, up 20 again, put us right here. Go over 1, up 20 more. Finally right here. So then we just connect our points. Alright, and so this line would represent a vehicle that's going 20 miles per gallon. Or that's getting 20 miles per gallon. Okay, so when you're comparing the two graphs, you want to look at two things. You want to look at the slope, and you want to look at the y-intercept. So let's start with the y-intercept. And notice in both scenarios, the y-intercept is at 0, meaning it crosses the y-axis at 0. And that should make sense. If you use 0 gallons of gasoline, then you would expect to go 0 miles, right? So that should make sense in both scenarios. Now, on the slope side of things, we got a little bit of a difference. In graph 1, we're going 25 miles per gallon. And on this one over here, we're going 20 miles per gallon. So we can say that the line is a little less steep on the second graph than it is on the first graph. This graph is rising faster than this line over here. Okay, based on our numbers. This one's going up 25 for every gallon. This one's going up 20 miles for every gallon. Okay, here's another example. This one says water is draining from a tank at a constant rate. The function h equals 6,000 minus 25x represents the number of gallons h of water in the tank after x minutes of draining. Okay, so h is the number of gallons of water in the tank after x minutes of draining. Write an equation that could represent the relationship between h and x if the amount of water in the tank before draining began increased by 1,500 gallons. Explain your equation. So what they're saying is, before this minus 25x even starts, before we start taking out the 25 gallons per minute, we're going to increase with the starting amount of water by 1,500 gallons. Okay, so we need to really understand what this equation's telling us to start with. What does each number in the equation represent? So here, the 6,000, okay, the 6,000, which is acting as my y-intercept, my b, right? It's representing the starting amount in the tank. Okay, it's how much water was in the tank to begin with. The minus 25, my slope, represents my rate of change, meaning that it is going down by 25 gallons per minute. So there's 6,000 gallons of water in the tank to start with, and we're going down by 25 gallons per minute. So the problem was to write a new equation with the starting amount that is increased by 1,500 gallons. So that means we're going to add 1,500 to our 6,000. Okay. Didn't say anything about the rate at which the water is draining. That didn't change. It stayed the same. So the only thing we're changing is this right here. So my new equation would still be H equals, instead of starting at 6,000 gallons in the tank, we're going to have it start at 7,500 gallons in the tank. And the water will still be draining at the same constant rate of 25 gallons per minute, with x being the number of minutes that's been draining. Okay, so if I were to look at the difference in the graph, this graph would have, the second graph here would have a much higher starting point, right? Because this graph would be starting at 7,500, whereas the first graph was only starting at 6,000. They would both be going down at the same rate, so the slopes of the two lines would be identical. Okay, but it's going to take longer to drain this second tank because there's more water to start with. Alright, so you expect it to take longer to drain out that water. Alright. So now let's take a look at this example here. We got a rectangle has a perimeter of 600 feet. The relationship between the length and the width of the rectangle can be represented by the function L equals 300 minus W. If the graph of the function changed so that the y-intercept had a decrease of 100, what would the perimeter of the rectangle need to be? Okay, so let's start with this first piece of information. Let's start with the known function first before we do anything to it. So we're talking about perimeter here, and we're talking about a rectangle. So we should be familiar with that formula. Perimeter of a rectangle is equal to twice the length plus twice the width. Okay. Or some of you guys may use this one. That's fine too. You can actually work this problem either way. It's just using a distributive property here to make it look a little different. Alright, and so if we fill in what we know for the original rectangle, the first one, we know it had a perimeter of 600. Okay, but that was when the relationship was the length was equal to 300 minus W. So I'm going to substitute in for L this 300 minus W. I'm just going to use this first equation. Alright, so I put 300 minus W where the L is, okay? We're just swapping those out, we're substituting. Now, if I simplify that a little bit, use my distributive property here. I get 600 minus 2W plus 2W. So you'll notice that the 2W's cancel out, right? You got a plus 2W and a minus 2W. Those are just opposites, so they just cancel each other out. Equals 0. So you can see that 600 equals 600. So if we use that along those same lines, we should be able to figure out what the new perimeter for our new rectangle is when we decrease the y-intercept by 100. So in our original function, L equals 300 minus W, again, if I'm thinking in terms of y equals mx plus b, remember the slope is the coefficient of x, and the b, which is our y-intercept, is just the constant. Well, in L equals 300 minus W, the 300 is my constant. My coefficient for x, which is my w in this one, is -1. Okay, if it helps, you can put the 1 there. So my m, my slope, is -1. My b is 300. So if I'm decreasing my y-intercept by 100, I'm decreasing this 300 by 100. So we're going to have 300 take away 100, giving us a new slope of 200. No, I'm sorry, not slope, I apologize. A new y-intercept. New y-intercept of 200. So that formula, that relationship, now becomes length is equal to 200 minus w. Okay, because we've decreased the y-intercept by 100. Alright, so how does that affect my perimeter? Well, I'm still using the same formula, but instead of putting 300 minus w here, we're going to put 200 minus w here. So now with this new rectangle, the perimeter is equal to 2 times 200 minus w plus 2l, or 2w, sorry, plus 2w. And again, using a distributive property, just like we did before, we'd see that perimeter is equal to 400 minus 2w plus 2w. And just as we did before, the w's cancel out. Minus 2w and a plus 2w. So you're left with perimeter equal to 400. So, by decreasing the y-intercept by 100, the overall effect on the perimeter was it actually decreased it by 200. Which should make sense, because if you think about it on a rectangle, if you are decreasing the length by 100 on both sides, and since perimeter is the distance around all four sides, well, if you decrease this side by 100 up here, and you decrease this side by 100 down here, the overall effect on the perimeter is you've actually decreased it by a total of 200. So going from 600 to 400 should make sense. Okay? Alright, final example here. We got a roof keeper kept data on the number of square feet he could roof during a day. The graph below shows the data he collected. So it says the roofer bought a new nail gun. He discovered he increased his number of square feet per hour by 50 square feet. So how would the graph change to represent the number of square feet he can roof with his new nail gun? Explain your answer. Alright, so he's increasing his number of square feet per hour. So that's a rate, feet per hour, right? So he's increased his rate by 50 square feet. So when we're looking at y equals mx plus b here, our rate is our m, right? It's our slope, our rate of change. So we're increasing this. This is the part that's going up by 50. Okay? So let's look at what his rate of change is right now. Now, be careful on how the intervals are marked. They're counting up by 0.5. So I'm going to go up to 1. So at 1 hour, he can do 200 square feet. So if we're going to increase that by 50 more square feet an hour, instead of getting 200 square feet done in an hour, he's going to have 250, right? So you just add 50 to the 200. So his new slope is 250 square feet per hour. So I'm going to put my new point right here, about midway between the 200 and 300. Okay, so if he's doing 250 square feet per hour, then at 2 hours, I would expect him to do 500 square feet, right? So that'd be another 250 square feet. And then at the next hour, he's going to do another 250, so that puts him at 750, which is a little bit off our graph up here. But you get the idea. Okay, so what effect did it have on the graph? Well, you notice it made the graph steeper. Again, because the rate of change is increased. Didn't change the y-intercept. You still would have 0 square feet done at 0 hours. However, the number of square feet he's getting done per hour is going up faster. Okay, this concludes our talk on the effects of rate of change and y-intercept in given scenarios. Thank you.